Statistical Process Control, SPC, is used to control a critical process output, acting on the factors affecting it only when required. The purpose is to differentiate between a statistically significant change in the process and common cause variation, because the actions required will be different. Process stability is a prerequisite for any further analysis. If a process is not stable, any conclusions you draw can't be assumed to hold in the future. With SPC, we check for process stability in the future. You can see this presentation in polyhedrica.blogspot. A case of overreaction is illustrated by the following example. Someone is shooting at a target, and based on the deviation of the impacts, he adjusts the gun sight after each shot. The result will be an increase of the dispersion of the impacts, therefore, the adjustments will make the process worse. The correct way is, of course, to fire 5 or 6 shots without adjustments and then decide if adjustment is required, based on the center of the impacts. This is an example of underreaction. If you drop a live frog into boiling water, it will immediately jump out to save its life. But if you put it in a pot of cold water and heat it slowly enough, the frog will eventually pass out without any reaction. Many companies have fallen into this trap. A big disaster generates a quick and effective response, and the company recovers. On the other hand, a slow degradation of their KPIs, such as customer sat or delays, pass undetected until it is too late. SPC uses some rules, developed by the Western Electric Company, to detect symptoms of statistically significant variation. The center line is the average of all values, and the standard deviation is also estimated from all the values. These are some examples of trend symptoms. The most obvious trend symptom is a value above the upper control limit, upward trend, or a value below the lower control limit, downward trend. We define zone A as the area 2 sigmas beyond the center line. 2 out of 3 consecutive values in zone A indicates a trend. If the values are above the center, it is an increased trend, and below the center, decrease. Zone B is the area 1 sigma beyond the center line. 4 out of 5 consecutive values in zone B is an indication of trend. 7 consecutive points increasing or decreasing is also a significant trend. In our charts, red dots indicate upward trend symptoms, and green dots downward. These are some upward symptoms definitions. This is an example of weight SPC. In this case, we are not using the actual graphical chart. We notice weight increase alerts up to 29/3 and weight decrease after the 1st of April. The conclusion is that we had a statistically significant weight decrease in this period. Whether this meets our slimming objective is another question. We will now analyze some of the charts used for variables and attributes. Download this Excel file spc.xlsx from OneDrive with the examples we will use. Since we collect a single value each hour, we are using a variables SPC chart for individuals. This chart can be complemented with a moving range chart, where the absolute value of differences between each value and the one preceding is plotted. We automatically apply the Western Electric rules for out-of-control symptoms, and the alert description will appear in the corresponding row 15 to 24. When any of these alerts appear, the corresponding point in the chart will be colored, in red, upward symptom, in green, downward symptom. While there are no colored dots, the process is stable, there are no statistically significant changes. We see green dots from 10 to 4 p.m. on April 10th, and red dots between 1 o'clock and 3 o'clock on April 11th, during the night. We can notice a jump from 16 to 5 p.m., which might indicate the moment when the process has changed, but this jump is not significant enough to declare it as a process change. It is not until 1 o'clock that we have enough evidence to declare that the process has changed. In this case, since we are measuring yield, an increase in yield is an improvement. So, we can say that process yield has improved sometime between 4 p.m. and 1 o'clock. With this information, we should now investigate what happened during this period that caused this improvement. How much have we improved? If we compute the average between 6 o'clock and 4 p.m., we get an average yield of 93. And from 17 to 11 o'clock the next day, 118. So, we can estimate an average yield increase of 25. Looking at the alert details in the bottom rows, we see that from 10 to 4 p.m., we have 4 out of 5 consecutive values 1 sigma below the center line, value significantly below the average. The value -9 at 2 p.m. means that the last 9 values were below the center line, same interpretation. The values 9 starting at 1 o'clock on April 11th mean that from 17 to 3 o'clock all values have been above the center line, yield has significantly increased. The SPC chart for individuals has a condition for the validity of the results. The data should follow a normal, Gaussian, distribution, so we will now check for the normality of this data with sheet basic stats. We see the histogram, which doesn't seem to have a bell shape, but the p-value 0.351 for the test of normality, well above alpha of 0.05, confirms that there is no evidence of lack of normality. The couple X bar and S is a common SPC pair chart for variables. Instead of making one single measurement each period, we make several, in this case 4. In this example, we have taken 4 measurements of a critical dimension every hour. Each hour, we compute the average and the standard deviation of these 4 measurements. We will plot the averages in one chart, and the standard deviation in another. We apply the same Western electric rules to each of the charts. Any out-of-control symptoms in one of the charts will indicate a significant process change. In this case, green or red dots in the average chart are equally bad, significant deviation from the average, which we try to center on the target value. In the case of the standard deviation chart, the interpretation is different. Red is bad, variation increase, and green is good, variation decrease. Operators must be trained to interpret these out-of-control situations to make the required corrections in the process as soon as possible.
Here we can see the specific symptoms alerting each out-of-control situation. The different symptoms may require different actions from the operator.
Looking at the chart, we can graphically detect an upward trend, which in this case of yield is a good thing. Our process is improving significantly from the statistical point of view. This trend is confirmed by the green dots up to 6 o'clock in day 11, followed by red dots starting at 12 o'clock until the end. The interpretation of this situation is that we have a continuous process improvement, starting around 11 o'clock on day 11, maybe due to some ongoing improvement actions. We can see the detail of the alerts in rows 15 to 24. Here we are collecting daily production data, and we notice that our average production is 400. Our individual's SPC chart is not detecting any significant changes in the process. On the other hand, we can see a repetitive cycle of 7 days, which of course, corresponds to a week. If we look in a calendar, the days of lowest production, we realize they correspond to Sundays, and the next lowest to Saturdays. This is telling us that maybe there is a significant seasonal trend within each week. To check that, we have added column DAO to our spreadsheet DAO2, where we calculate the day of the week, corresponding to each date with formula weekday, where A2 holds the date and 2 is to start counting the week on Monday. The confidence intervals for the average production each day of the week, 1 equals Monday, is. We can now confirm that there are significant differences in the production among the different days of the week. Wednesdays, 3, and Fridays, 5, have the highest productions. On Thursdays, 4, for some reason, it is significantly lower and, of course, It is lowest on Saturdays, 6, and Sundays, 7. We have been collecting process time daily during 3 months in sheet time, and we want to know if there are any significant changes during this period. Since we have a single value each day, we will use a variables SPC chart for individuals, time SPC. We need our values to follow a normal distribution to use this chart, so we will do a test for normality in basic stats time. We can clearly see a very skewed distribution, which is far from normal. This is also confirmed by the p-value of 0 in the normality test. This is what we would expect. Time measurements typically follow a skewed distribution for a simple reason. There is always a physical lower limit in time. On the other hand, there is no upper limit. Time may be extended by all sorts of defects or difficulties. This means we can't use an individual's chart. In this case, we can look for a data transformation that will make the data follow a normal distribution. This is a data transformation of the sort y equals x to the power of lambda, where we calculate the value of lambda to produce a normal distribution. We will calculate this value from the time data in column A of sheet box Cox. To calculate lambda, we will use Excel Solver. Calculate lambda in cell I8 by maximizing cell I6. The restrictions are lambda greater or equal than -5 and also smaller or equal than 5. The resulting value is lambda equals -0.3 for 8. In column F, we obtain the transformed data. We will now check if this transformed data follows indeed a normal distribution in sheet basic stats transformed. Checking the normality of this transformed data, we obtain a p-value 0.717, which confirms that this data is now normal, p greater than 0.05. Now we can use an individual's variables SPC chart with this transformed data in sheet SPC trans. So, we are controlling with SPC the transformed data instead of the original data, and we see no out-of-control symptoms in this case. Our process time is stable in spite of its high variance. This means it has not changed significantly along these 3 months. When we have a go-I-no-go check in our process, the data collected follows a binomial distribution. There are only 2 possible values. Then we can use a p-chart to control the proportion of defective units. In this case, we want to control the daily proportion of defective units, so we need to collect pairs of values each day. Sample size, number of units controlled during the day. Number of defective units found. The proportion of defectives, p equals defectives divided by sample size, is what we will control in the SPC chart. We can't just collect the proportions p because we need the sample size for the SPC calculations. If you look at the upper control limit in red, you notice that it is not a straight line in this case. The reason is that sample sizes are varying and this affects the control limit. The larger the sample size, the lower the limit. The average proportion of defectives is shown by the center line in blue, which in this case is 0.011% defectives. The same Western Electric out-of-control symptoms apply to this p-chart as before. We must distinguish between defectives and defects. A unit is either defective or it isn't, so the distribution of defectives is binomial, only 2 possible values. On the other hand, one unit may have more than one defect, so the distribution of defects follows a Poisson distribution. The aspect of a Poisson distribution may look like a variables distribution, but it is very different. The Poisson distribution only has integer numbers in the x-axis. An individual unit may have 2 defects or 3, but it couldn't have 2.8 defects. DPU can be any real number, greater or equal than 0. Sheet U has an example of a U-chart. In this case, the sample size is constant, therefore the upper control limit is a straight line. This information can be useful to understand the reason for these process improvements. Timestamps will let us associate changes we made in a line with the improvements. In sheet dist defects, we have used a pivot graph to plot the distribution of defects in the samples of 10. Average defects per sample of 10 is 4, so average DPU equals 0.4. These are some conclusions.
Real-time SPC is a useful tool for operators to control their process by making the required adjustments as soon as needed but without overreacting. Control charts are useless unless analysis and corrective actions are done in real time. To do this, data must be collected on the spot and charts updated fast enough. Operators need to be trained to know what corrective action is required in each case. Variables SPC charts of critical process parameters are more accurate than attributes, and they enable process adjustments before defects start to appear. Variables charts for individuals require normality, so you may need data transformation. Being in control is not enough. We must make sure the process meets the customer requirements. Process capability measures to what extent is a stable process able to meet these requirements.